Hi everyone. Today, we're diving into a fascinating topic: how to make Damerau-Levenshtein distance calculations much faster. This string similarity measure is incredibly useful, but it can be a real performance bottleneck. We'll explore several techniques to speed it up significantly. The Damerau-Levenshtein distance measures the minimum number of operations required to change one string into the other. These operations include insertions, deletions, substitutions, and transpositions of adjacent characters. It's widely used in spell checkers, fuzzy string matching, and bioinformatics. However, calculating this distance, especially for long strings or large datasets, can be very slow. The standard approach uses dynamic programming. It builds a matrix, or a grid, where each cell represents the cost of transforming a prefix of one string into a prefix of another. This method is correct, but its time and space complexity can be high. We need smarter ways to get results faster. One major improvement is early exit optimization. If you are only interested in distances up to a certain maximum, you can stop computing early. As you fill the matrix row by row, if the minimum cost in the current row exceeds your maximum allowed distance, you know the final distance will also be too high. You can then stop the calculation for that pair of strings. This saves many unnecessary computations. It's a simple but powerful trick. Another effective technique is bounded search, also known as the band or windowed approach. This method assumes that most differences between similar strings will occur close to the main diagonal of the matrix. Instead of computing the entire matrix, you only calculate cells within a narrow band around this diagonal. This drastically reduces the number of cells processed. It's perfect when you expect the strings to be mostly similar. For scenarios where you compare one string against many in a dictionary, using a tree, pronounced try, data structure can be incredibly efficient. You pre-process your dictionary into a tree. Then, as you traverse the tree, you can maintain the Damerau-Levenshtein distance for all possible prefixes. This avoids recalculating distances for common prefixes, leading to significant speedups for dictionary lookups. Parallelization is another powerful strategy. Modern computers have multiple processing cores. You can divide the work across these cores. For example, you can compute different parts of the distance matrix simultaneously. Or, if you're comparing many string pairs, you can assign different pairs to different cores. This harnesses the full power of your hardware. Furthermore, leveraging language-specific optimized libraries is crucial. Many programming languages offer highly optimized implementations of Damerau-Levenshtein. These are often written in lower-level languages like C or Rust. They are much faster than pure Python or JavaScript implementations. Always check if such a library exists for your chosen language. They often include many of the optimizations mentioned here. Finally, iterative deepening can be useful in specific cases. You start by searching for a small maximum distance. If no match is found, you increase the maximum distance and repeat. This can save time if you expect small distances and want to find them quickly without computing very large distances unnecessarily. These performance improvements make Damerau-Levenshtein practical for large-scale data processing and real-time applications. Thank you so much for watching this video. I hope you found these insights into optimizing Damerau-Levenshtein distance helpful for your projects. If you enjoyed this content and learned something new, please give this video a big thumbs up. It really helps the channel. And don't forget to subscribe for more videos on programming, algorithms, and performance tips. See you in the next